Hello everyone, my name is Ben Gamari, and I am a compiler engineer with Well-Typed. Today I'd like to demonstrate a new low-latency garbage collector, which we have introduced in GHC 8.10. Now, in recent years, GHC and Haskell as a whole has seen a considerable uptick in usage in server applications. Moreover, modern server applications tend to be components of distributed systems, where controlling the latency of each individual component of the system is crucial to maintaining overall system performance. However, GHC's existing garbage collector is ill-suited to latency-sensitive applications, particularly with large heap sizes. So, for instance, here we see a model server application, which I've run with GHC's -s runtime system flag. After execution, we see a few pieces of relevant information in the runtime system output. We see that the program produced a maximum residency of roughly 1.7 gigabytes. It took roughly 10 seconds to execute. And over the 13 major collections, on average, each stopped the mutator execution for roughly 400 or so milliseconds. In the worst case, the longest such collection stopped the program from running for nearly 2.5 seconds. Now, for many server applications, these sorts of interruptions are not acceptable. And a bit over 2 years ago, we were approached by a client to address this exact problem of long major collection pauses. So in this talk, we'll briefly review why these pauses exist, describe how our new low-latency collector avoids them, discuss who and why one might want to use this collector, and examine some benchmarks characterizing its performance on representative server workloads. So these long pauses that we saw above are due to the copying nature of GHC's existing garbage collector, which must pause the mutator while performing work that scales linearly with the size of the live on-heap data. To see why this is so, let's review quickly what a copying collector like GHC's does during collection. So here we see a simple heap consisting of 4 heap objects, A, B, C, and D. Each represented by a box. Of course, these can have references between them by way of pointers. And we see here that the mutator, the user program that is, contains a reference to A. And therefore A we consider to be a root. Perhaps this reference might sit on a thread stack, for instance. Now, to start a collection, we'll first pause the program and allocate a new region of memory, which we'll call toSpace. The idea here is that over the course of the collection, we'll move all live data from space into toSpace, updating any references between them as necessary. So to achieve this, we first start by traversing each root and copy it, each verbatim, into toSpace in a process known as evacuation. After copying a closure, we have replaced its from-space copy with a forwarding pointer referring to its evacuated copy, and update the reference we followed to find the closure. Later, we will return to each of the evacuated closures for scavenging, where we walk over each of the closure's pointers and evacuate each of the objects to which it refers. So here, we will evacuate B, moving it into toSpace, and later, when we scavenge B prime, we will evacuate C and D, giving rise to C prime and D prime. At this point, we've run out of things to scavenge, and consequently, we are done with collection. We can now throw away from space, freeing the memory associated with it, and allow the mutators to proceed with execution. Now, copying collection of this sort has a number of nice properties. It can be implemented with cheap allocation by way of a bump pointer allocator. This is quite nice for languages like Haskell, which allocate garbage at a rather prolific rate. It is efficient, as scavenging has excellent memory locality properties. It's compacting, which means we avoid the fragmentation of the heap over successive collections, and it can be easily implemented and parallelized. However, it's very hard to perform this sort of collection without a stop-the-world pause. And to see why, let's consider what might happen if we do allow interleaving of mutation with collection. So here we've returned to the example that we had previously, in particular the point at which we had evacuated A but not yet scavenged A prime. Say now that we allow the mutator to run, and at that point, the mutator will, for instance, read from A prime its pointer and use it to construct a new closure, X, which will naturally refer to B, which lives in from space. At this point, X, there is no way in which we could scavenge X, as X is not reachable from any of the objects that live in from space, and consequently, if we continue collection and eventually free from space, we'll end up with a dangling pointer. X will refer to B, which we've freed. This is the sort of issue that you run into when you try to incrementalize a copy and garbage collection scheme. And while there are many ways of dealing with this, they all generally come with some costs. Now, so when we sat down to design our collector for Haskell, we saw the need to balance the need for cheap allocation against ease of concurrent collection. And likewise, we wanted to ensure that we minimize the maintenance overhead that this new collector would impose upon GHC. Additionally, we wanted to avoid the need for recompilation, as this would be a tax upon our users. And so to achieve this balance, we sought to use a hybrid collection strategy. That is, we retain the existing moving collector for mutator allocations while promoting long-lived data to a non-moving oldest generation. This allows garbage to benefit from fast allocation provided by the moving generations, while facilitating concurrent mark and sweep collection of the oldest generation. Now the key bit here is that the only unbounded size generation is the non-moving generation, which we can collect concurrently. So while the moving generations still require stop-the-world pauses for collection, these collections are bounded length. Now, to achieve this, we relied on a design for a concurrent mark and sweep collector and heap structure that was described by Ueno and Ohori in their 2016 ICFP paper, which described a collection strategy that looks something like this. So here at the outset, we have two capabilities running mutator code when we realize we need to initiate a major garbage collection. At this point, we suspend mutation, and we begin evacuating data into the non-moving heap from the moving generations. We do this fairly aggressively, since we must, in order to reclaim any given object, it must live in the non-moving generation, during a major collection at least. So then we, after we've finished evacuating, we will collect a snapshot of the heap structure. We can do this very efficiently due to the nature of the heap structure. And this allows us to reconstruct the object liveness graph as even in the presence of concurrent mutation by the mutators. So after we've collected our snapshot, we enable a write barrier, which subjects the mutators to the need to do a bit of additional bookkeeping when mutating objects in the non-moving heap, and begin the concurrent marking phase. In this phase, we allow mutators to continue execution, but again under the influence of this write barrier, but then have, meanwhile, a concurrent marking thread will go and mark the live data in the non-moving generation until it has marked the entire heap, live heap that is, at which point we enter the final synchronization phase of collection, at which point we do a final round of marking any objects that were collected by the mutator's write barrier during the concurrent phase. And finally, we can disable the write barrier and allow the mutators to proceed with execution while we concurrently sweep the non-moving heap. So this is the general idea. How does one use it? Well, it's pretty straightforward. So here, returning to the example that we saw previously, for our model server application, we can just add the -- non-moving GC flag to our command line. after compiling with the threaded runtime system, which we have already done. And we allow the program to run, and we'll see that the runtime system report that results is very similar, but has a bit more information. So for one, we see that the maximum residency is similar, a bit higher. From 1.7 gigabytes, we went up to 1.9 gigabytes, and that's due to some overhead associated with the non-moving heap structure, as well as the conservative nature of marking. The total elapsed time is relatively unchanged, still around 10 seconds. And then we have, in the time-in section, a few additional rows. So as we see here, the major collections are relatively, the minor collections rather, are relatively unchanged. You have still a few milliseconds pauses, relatively inconsequential in the big scheme of things. But then we have these additional rows for the major collection pauses. Now these each correspond to phases of the major collection lifecycle that we saw in the previous slide. So our first line here corresponds to the preparatory pause. Here we see that the maximum pause in this case was only 1.5 milliseconds, down from, to remind you, around 400 milliseconds average, or 2.5 seconds maximum in the case of the copying collector. We're now down to 1.5 milliseconds for the preparatory pause. In the case of the final synchronization pause, even smaller, less than 1 millisecond. And this final line actually is not a pause at all, but rather corresponds to the duration of the concurrent phase of collection. And so we see here that it's a bit longer than the pauses associated with the major collection under the copying collector. But on the other hand, these are concurrent. So these aren't pauses, they're simply additional computation. That being said, we do have to keep in mind that throughout this entire 4-second pause, the mutator was under the influence of this write barrier, which does incur a bit of overhead. So there's perhaps a 4-second period in program execution where we were running a bit more slowly than we would have otherwise. But the point is that the program remains available and executing. These sorts of numbers are fairly typical of what we'd expect to see when under the non-moving collector. So here we see a latency histogram of a server application modeling a caching web server. This is not a latency distribution in the sense of garbage collection pause latency, but rather this is actually total end-to-end latency of the server application as measured by an HTTP load generator. So here we see a comparison of the moving and non-moving collectors run each in two configurations. A is a slightly 2 cores and 2,000 requests per second, and B is 8 cores and 8,000 requests per second. And we see here that in the 99.9th percentile, the latency distributions have diverged significantly, with the moving collections taking upwards of, or the moving collector rather, causing some requests to have latencies of well over 1 second, while in the non-moving case, latency remains hovering around 10 or 20 milliseconds. This is common. But in the case of typical of what you'd expect to see in the server application, however, and to clarify, the heap size of that previous benchmark was approximately 7 gigabytes rather. So it's a rather larger heap than what the example we'd previously seen. Now, in this slide, we're looking at the effect of fragmentation, which is something one must worry about when using a non-moving heap structure such as ours. Here we're looking at the occupancy, which is essentially the fraction of overall heap size that actually contains live useful data in the non-moving heap. And we're looking at this for 3 different size classes, object size classes, 2 to the 4, 2 to the 5, and 2 to the 6 bytes. As well as this pink point, these pink points, which are the overall occupancies integrated over all size classes. And we see here that over the course of this program run, which is an execution of GHC compiling the Cabal library, we see that occupancy remains around 75%. So about between 15 and 25% overhead due to fragmentation. This is, again, fairly typical of runs that we've seen. However, there is a bit of a cost that you pay in throughput, and part of that is due to the additional cost in allocation due to the non-moving allocator. As I mentioned earlier, the bump pointer allocator used by the moving collector is about the best case as far as modern hardware is concerned. However, the free list allocator that the non-moving heap uses is a bit more expensive. And we see that manifested in minor collection pause times, since the minor collector relies on the free list allocator during evacuation when using the non-moving collector. So here we see a histogram of minor collection pause times over two different benchmarks, search and map test. This is more of a server workload, search, and map test is more of a micro benchmark. And we see here that the minor collection pause time increases by between a factor of 2 and 4, I guess, is kind of a typical range. This is common and is part of the reason why we see a reduction in throughput, between 10 and 5 and 15% in throughput typically is the range that we often see. Some cases, no fib benchmarks in particular, are considerably worse in throughput, but they're not, they're quite poor as representatives of server workloads, so I tend not to worry about this too much. So in general, you can expect significantly lower latencies, a factor of between 5 and 50, but it's an asymptotic difference, so it's hard to give an upper bound. In latency, for most programs, server programs, especially in the tail. So worst case latency gets significantly lower. The throughput reduction tends to be around 10%, and this is generally due to locality as well as the write barrier overhead, which the mutator is subject to during concurrent marking. We see a memory footprint increase of between 10 and 25%, and that's in part due to the allocator overhead, in part due to the conservative nature of marking. And there's one other thing to keep in mind, though. Not all pauses are garbage collection pauses. So if you do see your program not a region of time where it's unavailable, it may be due to the garbage collector, and this is something you can determine with the event log, but it may also be due to unsafe foreign calls. This is something to keep in mind, and even foreign calls such as open can result in non-trivial pauses, especially if you're running against things like NFS, a file system with high latency. So something to keep in mind as you're looking at your server latency issues. So in general, there's a number of places where this is just a starting point. The current collector as present in 8.10 is sort of the minimal viable product, and we hope to be improving it markedly in the coming releases. There's a number of opportunities for optimization, both in throughput and pause reduction, as well as some opportunities for leveraging the new heap structure design to better accommodate things like pinned objects, which are currently a major source of fragmentation in some GHC compiled programs. So, in general, in conclusion, we have given a brief summary of the new low latency collector shipped in GHC 8.10. And I would like to acknowledge my colleague, Omer Sinan Agashan, for his help in getting this project off the ground. He was invaluable in this process. And to my partner, Laura, who is always around to bounce ideas around with, especially during the design phase. Numerous hours discussing various design options. And lastly, I'd like to thank Atsa Dijkstra and Pepe Ebora with our client for their help in testing and characterizing this new collector, and many kind interactions with them. So I would also point out that we have a paper at ISMM 2020, where we discuss more implementation details as well as give a more quantitative sense of the benchmark results that we see. So if you have more questions, feel free to ask now or see our paper. Talk to us, email me, ben@welltype.com. Be happy to answer. Thank you very much.